Hello, this is Graham, and it's the Tuesday, the 9th of July. Um, this is a very old program which I ran many, many years ago, and it's done in DOS because I had an old 386 when I wrote this. And this is a 488 iterations, and you can see this is just a few iterations past 477. These are the only symmetrical patterns. After that, it does become chaotic. But the rules for Langton's Ant, strangely, can be different as long as the rotation and the flipping of a colour is done. You will still get Langton's Ant. There will obviously be differences between where the ant is at a particular iteration, but generally speaking, the rules are: you move forward, and if you land on a white square, you turn right, and if it's a black square, you turn left, and you just invert the square that you're on. You don't necessarily have to do it that way. You can rotate and flip the color, or you can flip the color and rotate. It makes no difference where you rotate. You just offset the ant so that the event happens where it needs to be in order to follow the classic Langton's Ant that was done by Christopher Langton. So what we'll do is we'll just have a little run and see what that looks like when it's running. So there we are. I think 470, and we'll just leave that running for a second. I'm going to speed it up, and you can see that the chaos, there's nothing symmetrical about that. And then we'll take that to an extreme, and eventually the highway will begin, which is at around about 12,000. About 9976, I think, or 9977. Can't be sure. We're getting there. We're getting quite close to that now. And the highway now begins. Here we go. And you can see that the pattern, if you come back to here, you can see that this is here. So it's kind of just starting to show, but the repetitive pattern is obviously this, which is 104 iterations per loop, and this just goes on forever and ever and ever and ever. Now what I decided to do was to put that onto another program where I integrated. So every time there was a visit, I would turn it into a grayscale. So although we were just going black and white here, I decided to do a grayscale, and you can see this grayscale developing very, very slightly here. And the brighter the color, obviously, the more visits it's got. And this has 0 visits. So what I then did was I plotted the spectra. I wanted to know how many visits had 10 visits and how many there were that had 7 visits to get a graph of that. And so here is the height map. So we have 2 peaks here, and we got the 104 highway, and this is the spectral content. Now the interesting thing is that the sum, if you were to integrate this and get the sum of the area under this curve, that would match the total number of iterations that you've done, because obviously every single iteration will increment one of these bars by 1 depending on where you are. So what this means is that on this line, which is this one, it says that there are many visits at level 1, which obviously makes sense because this is the base. This is the base of the Langton's Ant. So that will give you this total of what's at the very, very base. The next graph will tell you how many there are at height 2. Now the thing about being at height 2 is it must have been at height 1 to get to height 2, which is why this is an area under the curve will give you the total number of iterations. If you differentiate this, you get the bell curve, which we can discuss in another video. But here you are with the magnitude of the spectra, and that's the magnitude of the spectra here. Under many iterations, what happens is this becomes an S curve. And if you do an infinite size lattice and you preload the lattice with 1s and 0s in equal number, that will get rid of a skew, and it will actually give you a very nice S curve, which if you if you differentiate, you will get your bell curve. In the limit, it's Gaussian. This is the program that I wrote, which allowed that to run for many, many, many iterations. And what we'll do is we'll just quickly spin that on, and you can see the 104 highway. This is grayscale, and you can see it fills up, and it's a continuum. Now on this particular one, it is it was 320 pixels by 226 or something like that, which is the old EGA screen graphics. And then I wrote another program which then ran for billions of iterations, and that one is all the way down here, and you can see this running. This is a huge number of iterations, and done in real time as well, because it was done in assembly language, so it was very, very fast. I think that's all there is to talk about on this particular one. The continuum just simply means that from there down to there, which is a graphics memory of so many bytes, it's continuous, or contiguous rather. And what that means is if you now wrap that around as a spiral onto a toroidal solenoid surface, you are modeling how an electron travels along a toroidal transformer. I might be able to very quickly add, bear with me a minute. There we go. We're going to add, I think I can do some drawings in here. I can do a scribble. Look, here we go. So if you take your line and you have your electron here, then if the electron hops 256 spaces, it ends up here. And if it then hops just one space, it ends up here. If we take this line and we put it into a coil like this, then what happens is this particular electron, which is sitting here, hops over 256, which ends up here. And if it does that, and it keeps doing that, what you're doing is you are modeling the magnetic induction across the coils. But more importantly, it's actually showing you the intercapacitance between the coils themselves. If you are going one step only, what you're actually doing is that on the coil, you are going from here to here and then to here. And then obviously, if you now take that and you turn it into a coil that does this, what you end up with then is you end up with that. And I think that's rather interesting, because you can now take that as a core sample of empty free space, and you can model mu naught, because mu naught is representing the magnetic field lines, which are doing this, aren't they, in this direction. And we know for a fact, and of course the electric fields are all coming off in this line. So you've got 256 nodes for the electric field lines, and then you have 256 field lines for that. And obviously when you take that to the limit of infinity and the lattice becomes infinity, you start to define the linear world of electromagnetics. What else do we have? I think that explains a lot. Thank you very much for listening.